Hello, this is Mr. Boothman again. Today we'll be talking about section 2.4, complex numbers. So let's go ahead and dive right in. First, let's talk about exactly what a complex number is. Well, let's start with an equation. Solve x squared plus 1 equals 0. Now, just looking at this, I can tell that something is a little off, right? How can I solve this problem? Well, subtract 1 from both sides. X squared equals negative 1. Take the square root of both sides. So I have x equals the square root of negative 1. I can't do anything with that. Square root of negative 1. How could I have a square root of a negative number? So we've been talking about domain a lot. We know that we can't have a negative number inside the square root sign. Why? Well, square root means that we have something times itself equals this number. So this means that something times itself equals negative 1. Well, if I have a negative number times a negative number, I'm going to get a positive number. If I have a positive number times a positive number, I'll get another positive number. So no matter what I do, I don't end up with a negative number when I multiply something by itself. That poses a problem for us. So a long time ago, mathematicians found a way around this, and they decided that we were going to define the square root of negative 1 as its own special number. So the imaginary unit I is defined by I squared equals negative 1. Or more simply, I equals the square root of negative 1. Now you might be sitting there asking yourself, why on earth would we care about this? I just said that there's really no number times itself that gives us negative 1. How can that make any sense? Well, the truth is that especially if you're sitting there watching this, you're a junior or senior, and you're thinking that you want to go into physics, you want to go into engineering, especially electrical engineering, there are a lot of places in real-world applications where we need to be able to take negative square roots. Don't ask me why. But there are. They show up all the time. And so we decided that, all right, in our number system, we are going to have this number, I, that takes care of this for us so that we can simplify these expressions and we can find our solutions. So that's where this comes from. That's why we use it. That's why it's important. Here, we define a complex number then as a plus bi, where a and b are real numbers. So here we have a is the real part of a complex number. So a is a real number, that means a is 2, or 100, or 1/2, or pi. A can be any real number. bi is the imaginary part. So again, b is a real number, so it could be 2, it could be 1/2, it could be the square root of 2. But I is this imaginary number, square root of negative 1. So complex numbers have these two components, a plus bi. Let's look at some examples of when we use complex numbers. So quadratic equations with complex solutions. I'm sure that we've seen before, and hopefully most of this complex number stuff is review for you. I'm sure that we've seen before that sometimes when we're finding solutions for a polynomial, we end up with a negative square root. We end up with solutions that don't really make much sense. And here are some examples of that. Of course, now we know that we can make sense of them using our complex imaginary numbers. So how do I solve this? I subtract 9 from both sides. I have x squared equals negative 9. And then I take the square root of both sides. So I have x equals the square root of negative 9. Remembering my radical rules, right? The square root of negative 9, that's the same as the square root of negative 1 times 9. With my radical rules, I can split that up into two different square roots. The square root of negative 1 times the square root of 9. The square root of 9 is plus or minus 3. We all know that. And again, it is plus or minus 3. When you take the square root, you get 2 solutions. And then the square root of negative 1 is I. So the solutions to this quadratic equation are plus or minus 3i. That's it. Pretty straightforward. So why don't you try B and C on your own? And we'll talk about these in class. For letter C, note that you're probably going to need to use the quadratic formula. So I'm not going to break into song and sing that for you, if that's how you learned the quadratic formula. It was how I learned it. But hopefully you remember that, and you can use that for letter C. Moving on, there are a few other places where we can finally put all of these pieces together and use our complex solutions to be able to solve fully polynomials. So first, let's take a look at this example. Example 2, use the rational zero theorem to find the solutions of each function. Now, hopefully, we've watched the 2.3 video, and so we know what the rational zero theorem is. So we know that we need P, which is going to be all the factors of our constant term, negative 15. So I have plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. Again, those are all the possible factors of negative 15. Q is going to be all the possible factors of my leading coefficient, which here is 1. So that's just plus or minus 1. How nice for me. That means P over Q is plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. So I need to now use synthetic division to test some of these numbers until I find one that leaves me with a remainder of 0, which means that that is a 0 for this polynomial function. So I'm going to try 5. 1, negative 2, negative 12, negative 15. Drop down my 1, that's 5, 3, 15, 3, 15, 0. So my remainder is 0. That means that my Q of x factors into x minus 5 and this, x squared plus 3x plus 3. So, what next? Well, I want to factor this completely and find all of my solutions, which means that I need to factor this. I can tell just by looking at it, so I'm going to use the quadratic formula. X equals negative 3 plus or minus the square root of 3 squared, which is 9, minus 4 times a, which is 1, times c, which is 3. So 4ac, that's 4 times 1 times 3, which is 12, all over 2 times a, which is 1. So I get x equals negative 3 plus or minus the square root of negative 3 over 2, which equals negative 3 plus or minus the square root of negative 1 times the square root of 3 over 2. Sorry, I guess I should be writing a little smaller. So I have x equals negative 3 plus or minus I square root of 3 over 2. So all my solutions to this function are x equals 5, and that was from my rational zero theorem, my synthetic division, and negative 3 plus or minus I square root of 3 over 2. Those are all my solutions. Note here that I have 3 solutions. X equals 5, x equals negative 3 plus I root 3 over 2, and x equals negative 3 minus I root 3 over 2. Note that the degree of this polynomial was 3. The degree was 3. I have 3 solutions. This is going to come up very shortly here for us when we talk about another important theorem. So that's how I use my rational zero theorem with my complex numbers, my imaginary solutions. So why don't you try letter B on your own? Again, we'll talk about that in class. But for now, we'll move on. This next part hopefully won't be too difficult. It's fairly straightforward. So I have to add or subtract two complex numbers, add or subtract their real parts and their imaginary parts. Real and imaginary. So we do it separately. And I'm not sure why all of my signs here disappeared, so I'm going to add them in. You should have them on your paper there. Okay, so I have 6 plus 3i minus 4 minus I. So I add or subtract, in this case subtract, my real parts, 6 and 4. So 6 minus 4 is 2. And then my imaginary parts, plus 3i minus negative I. So that's plus 3i plus I, which is plus 4i. And that's my solution. Pretty straightforward. So why don't you try B and C on your own? Get some good practice in. And we'll move on to multiplying. Here we use the distributive property to multiply two complex numbers, and then we simplify them and collect their like terms. So here I have 4i times negative 6 plus I. I need to use the distributive property, so 4i times negative 6, that's negative 24i. And then 4i times plus positive I is plus 4i squared. I squared, we said way up here, is defined as negative 1. So this is the same as negative 24i plus 4 times negative 1, which is negative 24i minus 4. So if I write this in my a plus bi order, this is negative 4 minus 24i. Again, fairly straightforward. So try B and C on your own. We'll talk about those in class. Hopefully they're not too difficult for you. And we will finish with dividing. So when there is an imaginary number in the denominator, we multiply the top and the bottom by the same complex conjugate of the denominator. So if this isn't much of a review for you, if you're learning this for the first time, or if you just forgot what a conjugate is, I'll explain. The conjugate for a complex number, so say we have a plus bi, the complex conjugate is a minus bi. We switch the sign. So if I had a minus bi, my complex conjugate would be a plus bi. So let me work through one last example for you. Let's try dividing this problem. 6 plus 4i over 2 plus I. My complex conjugate of the denominator, 2 plus I, is going to be 2 minus I. So I need to multiply this fraction by 2 minus I over 2 minus I. Note that I have 2 minus I over 2 minus I. That's something over itself that's 1, which I'm allowed to do to anything. That's why I'm doing this. I can multiply anything by 1. So if I distribute here, 6 plus 4i times 2 minus I, that's 12 plus 8i minus 6i minus 4i squared, all over, I do the same to the denominator, 4 plus 2i minus 2i minus I squared. And now I combine all my like terms and I simplify. I have 12 plus 2i minus 4, and we said that I squared is the same as negative 1, all over 4 plus 2i minus 2i goes away, minus I squared is negative 1. So I have 12, negative 4 times negative 1 is positive 4, so 12 plus 4 is 16, plus 2i all over 5. And that's how I divide complex numbers. So again, try B and C on your own, and we'll talk about those in class on Tuesday. If you have any questions, be sure that you're writing them down. Be sure that you go back and rewatch parts of this that were confusing to you, that you don't understand, and bring your questions to me, to Miss Parker, on Tuesday, and we'll be more than happy to go over them with you. In the meantime, I hope you're having a great weekend, and I'll see you in class on Monday. Thank you all.